In this section of chapter 9, we will discuss about electron domain and molecular geometry and shapes due to 2 to 4 electron pair or electron domain on central atom. The electron domain could be due to each electron domain could be just due to a single pair of electron or more than one pair if they're concentrated in one direction. We'll talk more about these. Let's for the time being assume one electron domain is due to one electron pair on the central atom. We can predict shapes quite readily when there are two pairs of electrons. Let me show you that. If this is my central atom, and let's have two pairs of electrons like this. Keep in mind that electrons are negatively charged and they repel each other. So they're going to repel each other and try to stay away from each other. So electron pairs are like bad neighbors. The neighbors want to stay farthest away from each other. So within this area, circular area, the farthest they can go could be, you all know, it'll be like this. And our central atom remained the same. So this would be the best shape due to electron pairs. And the angle is, you all know, this is 180 degree. Now let's think about the case when we have three pairs of electrons or three electron domains. So this is my central atom. Here I'm pretty sure that you'd be able to predict what could be the shape. Let's put these three pairs close to each other. Again, knowing the fact that each pair of electron is repelling the other pair, so they would try to be farthest away from each other. You can quickly find out they'll be farthest from each other when their geometry or shape is like this. Let's have the central atom, and then I'm going to write down three pairs of electrons. You can try it at home. This is only how you can get electron pairs farthest away from each other because they repel each other. And so the best geometry due to electron pair would have 120 degree angle. So each of these angles would be 120 degree. And the name of the shape is called trigonal planar. Now keep in mind these are shape due to electron pairs. Nothing has been bonded yet. In this slide, again, I'm going to review this, what I just mentioned. What determines the shape of a molecule is electron pairs. Whether they are bonding or non-bonding, they all repel each other. And we already mentioned that electron pairs should be placed as far as possible from each other. So that's how we get the linear trigonal planar. With four pairs, many of you may come up with the wrong answer. This is a common answer. Let me first write down what students commonly think. Even at your level, I used to think that way too. If there are four pairs, there is a common thinking that four pairs would be like this. Because we are more used to thinking in terms of a planar structure. It sits on a plane, each angle is 90 degree. But if you make a model, if you have a chemical model, you know this is not the best structure because these pairs of electrons can be farther away from each other, which is 109.5. So this is not the best structure. So the best structure is going to look like this. So let me draw it again. I have little space on the left hand side. So I'm going to use that space. Central atom is red. And then I'm going to show you four pairs. One pair, two pair, three pair, four pair. With molecular model, you'd see it better. Each angle is 109.5, so it's greater than 90 degree. And it's a three-dimensional structure. It's not going to sit on a plane of paper. So that's how you get this structure. For 5 pairs of electrons, again, this gets a little bit harder to imagine because there are now trigonal planar and 1 pair on the top, 1 pair on the bottom. It's called trigonal bipyramidal structure. And for 6 pairs, it would look like this. It's called octahedral. As you can see, that octahedral structure, each angle is 90 degrees. Now here we're defining electron domain and electron pair. This is a hypothetical situation. I have a double bond here directed in between A and B. So it's like directed in between A and B, and that would be considered to be a single electron domain. So in a double bond or triple bond between 2 atoms would be considered to be a single electron domain and behave like as if there is an electron pair. So keep that in mind. In this case, central atom has 1 electron domain, the second domain, third domain, and the fourth domain is non-bonding electron pair. So you see here simply electron pair in 3 cases. Let me have red mark on it. These are 1 electron pair, 1 electron pair, 1 electron pair, and those 3 electron pairs made 3 electron domains. But 2 electron pairs makes the 4th electron domain. Again, based on valence shell electron pair repulsion theory, we came up with already those answers. With 2 electron pairs, we get linear shape due to electron pairs. 3, we get trigonal planar. With 4, you get tetrahedral. 5, we get trigonal bipyramidal, and 6, we get octahedral. We don't need to go beyond that. Let's now go over examples. Now we'll begin with beryllium fluoride, BeF2. First, you need to write down the valence electrons. By looking at periodic table, you can quickly get the number of valence electrons. For example, beryllium, it appears in line 2 of periodic table. So start counting from the beginning of line 2 until you reach beryllium. So what you're going to find is the second element in line 2, and that's why beryllium would have 2 valence electrons. So let me write down. So beryllium would have two valence electrons. Now each fluorine again appears in line 2, but that's if we count from the beginning of the line. 1, 2, 3, 4, 5, 6, 7 is the 7th element. So each fluorine would have 7 valence electrons, and there are 2 such fluorine, so that'd be 14, and 2 valence electrons coming from beryllium. So 14 plus 2, 16. So hopefully you know that how I counted the valence electrons. So there are 16 valence electrons. Now let's write down central atom, which is Be. At this point I don't know the shape, so I'm going to write down any way I want, because Lewis structure doesn't care about the shape. In any shape you can write down. Now if you go through the rule, first you need to give noble gas configuration to the outer atoms except hydrogen. Of course hydrogen gets helium configuration as soon as there is 1 bond. For other elements, noble gas configuration means altogether 8 electrons or 4 pairs of electrons. Let's do that now. I'm going to use a different color so that you see these electron pairs. Each line means a pair of electron. So that makes 16, or I'm sorry, it's 4 pairs of electrons. So it'll be 4 pairs of electrons now around each fluorine. Altogether now we have 16 electrons assigned, and I don't have any extra electron to give noble gas configuration to the central atom. Also, we're not supposed to make double bond here because experimental evidence suggests that there is no double bond between beryllium and fluorine. This is one of those exceptions where central atom doesn't get noble gas configuration. So with this in mind, let's try to understand the shape of this compound. Now assume that for the time being fluorine are gone, but electron pair is going to stay in between beryllium and fluorine that was holding the bond, that was holding the fluorine. Now, this is how it's going to look like. When fluorine is gone, leaving behind its electron pair that it shared with beryllium, this is how it's going to look like. Electron pair here, second electron pair here. And we all know that electron pairs repel each other. And so it's not going to be the best shape. The best shape would be given by beryllium with pairs of electrons on completely opposite side at 180 degrees from each other. Now let's bring back fluorine. So these electron pair would act like glue. The fluorine can only be bonded at these directions where these electron pairs are present. So one fluorine is going to come over here, the other fluorine is going to come over here, and you get a linear molecule. And so you know that beryllium fluoride would have a linear geometry. Let's now work on SO3. SO3, let's write down here first. SO3, again, let's first count valence electron. Sulfur appears in line 3. Let's count from left to the right, from the beginning of line 3 until you get sulfur. 1, 2, 3, 4, 5, 6. So there are 6 valence electrons on sulfur, plus oxygen has, again, oxygen appears in line 2 of periodic table. And let's count it from the beginning of line 2. 1, 2, 3, 4, 5, 6. So each oxygen would have 6 electrons, and there are 3 such oxygens, so 6 times 3. So altogether, we must account for 24 electrons. These are the valence electrons. Now, central atom is sulfur, and outer atoms are oxygen. So let's now draw these. So I would have sulfur. Let's make a room here. Sulfur. And I can write any way I want. Oxygen, oxygen, oxygen. Now, I now need to give noble gas configuration to oxygen atoms. That means I need to assign 3 more electron pairs around each oxygen. So as I said, each of my line represents 1 pair of electron. Now let's count now. So I have assigned 24 electrons, and we did have 24 electrons. But the only problem is central atom doesn't have 8 electrons. It has 6 electrons, the way I have drawn it. So in order to give it 8 electrons around the central atom, bring 1 electron pair from oxygen to in between sulfur and oxygen. Now that's going to give following structures that I'm going to draw next. S, O, O, and double bonded O. Now let's try to find out what kind of geometry or shape you would have. Now double bond, it would act as a single electron domain. So basically you'd be counting as if there are 3 electron domains around sulfur, and 3 domains would give you this kind of shape. Sulfur with 120 degree angle, and now stick in oxygen, 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 and you have a double bond in here, and that's it. That is SO3, and it would behave as if there are 3 electron pairs or 3 electron domains. So angles are all 120 degree, and this is called trigonal planar structure. In the same way, you can work on one of those other compounds like NH4+, where you'd have 4 pairs of electrons around the central atom and they'd be all bonded, giving a tetrahedral geometry. Now here we're showing you NH3 bonding, and then we're determining the shape of this compound. This is the Lewis structure of NH3. After having 3 hydrogens, then there is 1 pair of electron on nitrogen. So altogether, now think about for the moment, hydrogens are gone, but it left behind electron pairs on nitrogen. So we have altogether 4 pairs of electrons around nitrogen, and 4 pairs would give tetrahedral geometry. So basically it would look like this, and 1 pair like this, 2 pair, 3 pair, and then another pair going away from us. So this is how it would look like. Then bring back hydrogens. Now hydrogen can take any of those 3 locations. They're all identical. Without a model, it'd be often hard to understand that they're identical. So let's stick in 1 hydrogen here, another hydrogen here, another hydrogen here. So that's how we get NH3 with 1 pair of electrons sitting on nitrogen. So electron pair geometry with 4 pairs of electrons would be tetrahedral. That's electron domain geometry. But when you take the picture of the molecule, you're not going to see electron pair. What you're going to see would be just 3 hydrogens. So looking at the right hand side structure or shape of this molecule, assume that this is gone. So if something is missing, one object is missing from a tetrahedral structure, then it would no longer be a tetrahedral structure. So it would look like a trigonal pyramid. So this is the part you're going to see when you take the picture of the molecule when there is electron pair, because you don't see the electron pair, you're only going to see those atoms. So even though electron domain geometry is tetrahedral, but molecular geometry is, in this case, is going to be trigonal pyramidal, because you have a triangular base here and nitrogen is on the top of that. So keep this in mind. Electron pair geometry and molecular geometry are not always identical, especially when all those electron pairs are not bonded. When all those electron pairs are bonded, then electron pair geometry would be same as molecular geometry. So this is something that I already mentioned in last slide, so we're not going to spend much time on this, but you're seeing the picture again. Again, from you can see that how from tetrahedral structure you can get trigonal pyramidal. I can also remove another atom leaving behind the electrons. So I would still have electron pair here, another electron pair here. And if I take the picture of the molecule, it would not look like tetrahedral because 2 objects are gone from 2 corners of a tetrahedron. So it would be nonlinear or bent. So make sure you know these names, even though you still have 4 pairs of electrons. Looking at the middle structure, again you have the pairs of electron there, but there is nothing is bonded there. So when you take the picture, you'd only see the bonded atoms, and it would look like trigonal pyramidal. In first case, all those electron pairs are bonded, and that's why molecular shape in first case is going to be tetrahedral. So from tetrahedral you can get trigonal pyramidal and bent or nonlinear shape as you keep on moving away the bonded atoms, leaving behind its electron pair. Again, this is an example of carbon dioxide here. Look at here. Even though carbon dioxide has 2 double bonds on 2 sides, but they would be counted as 2 domains of electrons. So for 2 electron domains would behave like 2 electron pairs. So that would be a linear geometry. And so carbon dioxide would have a linear structure with angle, OCO angle is 180 degrees. So this is 180 degree. Now we already discussed this about trigonal planar with 3 pairs of electrons or 3 electron domains, and by removing one of those you get a bent or nonlinear shape. So keep this in mind. When all the electron pairs are bonded, electron pair geometry or electron domain geometry is the same as molecular geometry. If anything is missing, if one is missing, then it becomes bent. And that's the case you get in case of NO2 minus. In NO2 minus, you have one double bond, and that be counted as a single electron pair, and so or single electron domain. And the second domain, let me draw those arrows so that you can see that. This is one electron domain, this is the second electron domain, and the third domain is the non-bonding electron pairs solely sitting on nitrogen. So it's 3 electron domains, but one of the bonded atom is not there. So it would look like a bent structure. If you had the bonded atom, it would be trigonal planar geometry. Now, how non-bonding atom can influence the bond angle, that's what we are showing you here. In first example, we have methane. Angle is 109.5 degree because it's a tetrahedral structure. All the electron pairs are bonded. In case of NH3, only 3 hydrogens bond those tetrahedrally directed 4 pairs of electrons. Even though electron domain geometry in each case is tetrahedron, but molecular geometry is not the same. In case of ammonia, one bonding atom is missing, and when you take the picture, it will be trigonal pyramidal, which we discussed before. In case of H2O, again, there are 4 pairs of electrons around oxygen, but there are only 2 bonded atoms. So still, angles are pretty much set by those 4 pairs of electrons. Normally, you'd expect 109.5, but these unshared electron pairs or non-bonding electron pairs push those bonding electron pairs to a smaller angle. So this angle is no longer 109.5, rather it's slightly smaller than that, and that's why it's 104.5. You don't need to memorize these angles. I'm talking about especially those smaller angles smaller than 109.5. If you just know that it's smaller than 109.5, that will be good enough. In case of ammonia, also the angle is not 109.5, it's 107 degrees, smaller than that because there is one non-bonding electron pair. 2 non-bonding pair in case of water squeezes the angle even further from 109 to 104.5 degree. Again, by now you already know how to deal with this, but there's a slight difference that you can see here. Even though we said we're going to count a double bond as a single electron domain, but there is a subtle difference. If it is 100% like a pair of electrons, then your angle would be 120 degrees each. But the double bond, the pi bond, makes some difference in this angle. It tends to squeeze the other angles, and that's why the angle is no longer 120 degrees, rather it's 111 degrees of the other bond angle. And in addition, these angles got slightly bigger. Again, this is the effect of this pi electron cloud. But approximately you can still say that these are 120 degrees, close to 120 degrees. Tetrahedral electron domain, you can see here tetrahedral electron domain. I already mentioned about all these examples. Like first one is methane, the ammonia with 1 pair of electrons sitting on nitrogen, and then water with 2 pairs of electrons, non-bonding electron pairs sitting on oxygen. So even though electron domain geometry is tetrahedral in each case. So in case of methane, all atoms, all of those pairs of electrons are bonded, so it's also tetrahedral. So this is tetrahedral. But then in case of ammonia, one is missing, so it's trigonal pyramidal. In water, two of those corners are missing from tetrahedron, so it's bent or nonlinear geometry. So the key point that I'm trying to make is, even though angles are pretty much set by pairs of electrons, the shape would not be identical to shape due to electron pairs in many cases, especially when they're not all bonded. Always imagine you're taking a picture of the molecule when you're thinking about shape of molecule, and cover those electron pairs sitting solely on the central atom. Then you have an idea what could be the shape of that compound.